Yes guys, question 3 now. I'm thinking of a number. All I give you that if I triple this number, it leaves a remainder of 13 when divided by 17. Unfortunately, this is clearly not enough information to figure out my number, well obviously. However, it is enough information to figure out what the remainder of my original number is when divided by 17. What is this remainder? Alright, let's try converting this really lengthy, wordy problem into some maths. Right, we'll give you that if I triple my number, it leaves a remainder of 13 when divided by 17. So let n be this number, n equal number. The number's what? Just a positive integer. Well, not even a positive integer, just an integer. So we say 3 times this number, it leaves a remainder of 13 when divided by 17. So it's some multiple of 17 plus 13. That's our first piece of information. However, it is enough for me to figure out that the remainder of my original number is, what the remainder of my original number is when divided by 17. So n equals 17, or another scalar of 17, so let's use j plus r, and we are trying to find out r here, where r is the remainder. So we can somehow make a link with these two equations using n. So we know that 3n equals n plus n plus n. So 3n equals 17k plus 13. N equals 17j r, well, 3 times. So we expand 17k plus 13 equals 51r plus 3r. Now, we need to work in mod 17. Why? Because this way we can eliminate these scalars k and not r, should have been a j. Should have been a j. We can remove these scalars and find an expression only in terms of our remainder, which we're looking for. So if we apply mod 17 to this, 13 is congruent to 3r mod 17. So now we just have to test values that work. So we can rewrite the statement as 3 3r equals 17. Actually, I'll just leave that. Let's just try subbing values for r. Let's not try to complicate this. So we're told that r can be anything between 9, 10, 11, 12, 13. So let's try 9. 3 times 9 is 27. 27 mod 17 is 10, which is not 13. So we can put next number, which is 9. Let's try 10. 13 is congruent to 3 times 10, which is 30 mod 17. 30 mod 17 is just 13. So we can say when r equals 10, 13 is congruent to 17. 3 times 10, 13 is congruent to 30 times 30 mod 17, which means 13 is congruent to 13 mod 17, and this is a true statement. Therefore, our answer is B. Nice. Question 4. Here we're required to prove the divisibility rule for 11. If n equals a0, a1 up to an is a positive integer, then n is divisible by 11 if and only if a0 minus a1 plus a2 minus plus an to the minus 1 to the n is also divisible by 11. Well, a few things I notice is the following. We've got alternating signs between every term, and the way this can come from is from the minus 1 to the n, because minus 1 to the n can either be minus 1 or positive 1. So this is a good thing to keep in mind. So let's write out what n actually is. So we're told it's a0, a1, a2, an, let's separate each digit. So n equals, well, minus 1 to the n, a 0 plus minus, sorry no, do not minus 1 to the n is equal to 10 to the n, that's how many digits there are, right? A0, so that's whatever thousand millions times A0 plus 10 to the n minus 1 multiplied by A1, and so on and so forth up until 10 to the 0 an. Now we need to show that this is divisible by 11, so obviously we need to work in mod 11. Now notice 10 to the n is congruent to minus 1 to the n mod 11. This is where this minus 1 to the n kicks in. I think that will be useful now really. So n is congruent to mod 11 minus 1 to the n a0 plus minus 1 to the n minus 1 n minus 1 a1 up until minus 1 to the 0 an. Now we can factorize out minus 1 to the n. So if we bring this minus 1 to the n to the front, well, we know minus 1 to the n is either going to be positive or negative. So let's assume that it's positive, minus 1 to the n. Sorry, we're assuming that n is either even or odd. So when n is even, we have minus 1 to the n plus a, actually we can just do this generally, so we can say minus 1 to the n is being factorized out, so we have a0 plus, well, minus a1. We have to switch signs because if we go from even to odd or odd to even, minus 1 becomes minus 1 or 1, or minus 1 or 1. We're just bouncing between these two numbers. We have plus a2 up until minus a to the n. And since we're doing minus 1 divided by minus 1 to the 0, which is just 1, divided by minus 1 to the n, we have simply just minus 1 to the n. Now, we know that minus 1 to the n is either equal to plus or minus 1, so we can say that our expression here is equal to plus or minus all of this and n. So we say n is congruent to all of this mod 11. Now this plus or minus, when working with mod right, we know that any number is congruent to itself, mod x, where x can be any real, and it's also congruent to minus n, minus n mod x for any real. So we can just use an example. 7 is congruent to 8 mod 7, and 7 is also congruent to minus 7. Is this correct? Let's check. Minus 1. Yeah, it's all good. So we can say now that n is some multiple of k, where k is this statement here. So we can say that 11 divides n, and let's go back above. N was a0 minus a1 plus a2 up until minus, this should have been a positive because we started off with positive, so we needed to end in positive. That was a mistake. Let's change that now. Alright then, that's all that was. Bit of a complex problem. but all good.